Here we go. Alright, so hello everybody. Gillard and I are from, or I'm Eric, and I'm here with Gillard, and we're part of the GatorBytes, and today we're going to be helping teach about robot design strategy. What is the first thing that we should look at when beginning to strategize for a season? Since the tasks and point totals are different each year, the approach of a team to the game, the robot, and their software will be different. Some of the things that could influence decisions include cycles, which does the game require cycling or a more prolonged task? Alliance role. In many seasons, there are two main objectives a team could choose to accomplish. A team will often choose A team will often choose what they think they will do best at. Robot size. Generally, a robot will push the 18 by 18 by 18 size limit. However, in some seasons, such as Freight Frenzy, robots were much smaller. And endgame. Do the endgame tasks require a very specialized assembly? Parking often doesn't, but a capping mechanism might.
Right, cycles, speed versus reliability. Often a game will have some sort of task that must be done over and over. Some examples include Freight Frenzy Alliance Hub, Ultimate Gold Tower Goals, Rover Ruckus Lander, and Velocity Vortex Shooting. In each of these games, alliances had to do their tasks repeatedly, often over 20 times per match to win at the highest level. Points increased linearly. Other times, a game will have a task that will still repetitive, takes a bit longer to do. Some examples include Skystone stacking, relic recovery ciphers, cascade effect ball towers, and for these tasks, point often increase exponentially, meaning that the task needs to be completed every time for team consistency.
Alliance roles. Sometimes a game will have two specific tasks that robots must be able to do to score the most points possible. Some examples include Freight Frenzy Shared, Alliance and Skystone Stacking, and Feeding. A team often needs to design a robot that is specific in one area, or one that is able to do both tasks, but that can be much harder to do well. So on the left side, there's the Alliance design robot with I believe that is our robot, versus the shared design robot, which is the Brainstorms robot.
A robot size. Game Manual 1 dictates that robots must be no larger than 18 inches by 18 inches by 18 inches to pass inspection. In most games, teams push their robots to the max. However, for some games, such as Freight Frenzy, teams have much smaller robots. In the case of Freight Frenzy, some teams chose to use a smaller robot, 12 inches by 12-inch drive base, which allowed them to save time by traversing the gap rather than going over the barriers. So on the left, we have a full-size robot, which is pretty. There's a lot of things going on there with using the max size 18 by 18 inch by 18 inches, and compared to a smaller robot, which mostly compacted it and made it a little bit taller, going 12 inches by 12 inches, but maintaining the same height to uh, allow for more things to be put on it.
Endgame tasks. Tasks in endgame are normally worth more points than normal teleop tasks. For example, in Freight Frenzy, during endgame you could deliver ducks to the field, 6 points each. A good team could deliver all of the ducks in 20 to 24 seconds, netting the Alliance 60 points, which was equivalent to cycling 10 cargo to the Alliance hub. The time that was saved was very useful as it allowed the robot to cap and or go park. When designing your robot, you might want to prioritize an endgame task to allow your alliance to be sure that you score the maximum points possible.
Hornet robot design aspects. When building a robot, there are many different ways to approach the task at hand, and often there's no one best design. The following few slides is going to detail mechanisms that are important to understand when designing robots. So we have a drivetrain, power transmission, active intakes, linear motion, arms, choosing a motor, and choosing servos.
Drivetrains. For your drivetrain, there are two main options: a tank drivetrain and a holonomic drive. A tank drive, as suggested by its name, drives like a tank. It normally has very high traction and can drive over obstacles easily. Tank drives are often in 4 or 6 wheel drive variants. Holonomic drives are special as they can not only drive like a tank but also move side to side, allowing for high maneuverability. The only common holonomic drive is mechanism wheels.
Power transmission. For driving a drivetrain or other robot mechanism, there are 4 options for the power transfer needed to drive said assembly. So we have a direct drive, gears, chain, and belts. So I think our top picture is a chain drive, mainly I think for a tank. And on our bottom left is a belt, which is used. And for our middle picture, I believe that is a direct drive, which is connected mostly to the motor or close to the motor. And then we have our gear drive on the bottom right.
Power transmission, direct drive. The simplest way to drive a wheel or other mechanism. A direct drive system is where the component being driven and attached being drive and attached directly to the output shaft of the drive motor. While a direct drive system is easy to implement, it is often weaker than other types of power transmission, as the gearbox of the motor has a higher chance of breaking if a shock load is transmitted to the drive shaft. The best way to support a direct drive system is by attaching a shaft coupler to the motor and supporting the drive shaft with something such as a channel. So to the left photo we have the best direct drive. The middle picture is an okay example of a direct drive, and then the right photo is a bad example of a direct drive.
All right, gears. There are 3 main types of gears that are available for use in FTC. So we have spur gears, bevel gears, miter gears for 1:1 ratios, and worm gears. Using these 3 different types of gears, you can easily create low to high ratios for more or less torque. The one thing that you need to be careful of is the mesh of your gears, as a bad mesh can cause either slippage or high wear.
Chains. Chain is a great method for powering a system over a distance. Chain can easily be lengthened or shortened using a chain brake and or master links. The only issue that chain has is that it tends to stretch over time and the sprockets are quite big when making a reduction.
Alright, belts. Belts are often considered the best form of power transmission, especially over long distances. The main upsides to belts are the weight savings and the versatility for ratios with 3D printed pulleys. While while there are a few good upsides to belts, it is a more complex transmission system, requiring teams to plan out where their belt runs will be, which is often done in a CAD software. Belts are often very cheap, as vendors such as V Belt Guys have common belt sizes for $1.50 to $7.
Intakes. When picking up a game element, it is often recommended that bots utilize an intake to collect game elements. These are 2 main types of intake. There are 2 main types of intakes: vertical, noodle intakes, and horizontal, compliant wheel intakes. Vertical intakes are best suited for picking up smaller game elements, while horizontal intakes are best for picking up larger game elements. So the left photo is an example of a noodle intake, whilst the right one is a compliant wheel intake.
Linear motion. Most FTC games require some sort of linear extension. Rather than using an arm, many teams resort to using a linear extension, as it is much less complicated in most cases. There are 2 main types of linear extensions: slides and lead screws. Slide extensions are often made from draw slides or extrusion and are great for long-reaching tasks as these systems are light and easy to power. These screws are good for high torque situations such as the climb task in Rover Ruckus.
Arms. If a team cannot use a linear extension for some reason, they often resort to using arms. Arms are hard to get working efficiently on a large scale due to their weight and other issues on the programming side. Standard arms are the simplest form of arms, as they are just a bar on a powered shaft. 4 bars and double inverse 4 bars are better in many cases, but require more parts and are more complicated to get working well.
Right, choosing motors. There are many options for motors on the market to choose from. With planetary gearboxes easily available, we don't recommend using spur gearboxes. Below are some of the motors that our team recommends using. So we have Rev Ultraplanetary, configurable gearbox allowing for easy changing, which I believe is the bottom left. Go Build a Yellow Jacket, 11 ratios, or 1-to-1 ratios, I think. 3 output shafts and 16mm patterns, which is the middle. And Andy Mark Nav Rest, 5 ratios, basically a GBYJ with different pattern, which is the bottom right.
Choosing servos. There are hundreds of servos on the market, from cheaper $15 servos all the way up to 449 monsters. For 99% of FTC of FTC applications, Go Builda's torque, speed, and super speed servos are great. Our team used all Go Builda servos last year. In the very rare case in which you need more torque or speed, Savo makes some amazing servos. However, they are quite pricey for FTC, $150. That's basically it, and this is our contact info in case you want to reach out to us. Our team Instagram is at GatorBytesFTC, and team email is GatorRoboticsFTC@gmail.com. Any questions?
Are there any different types of arms besides the ones that you showed?
Um, I'm fairly sure there might be, but the most common ones are going to be the standard arm, the 4 bar, and the double inverse 4 bar. Those are just the only ones that I know. Any other questions?
Um, so for this year's game, it looks like linear motion will probably just be like the main thing, right? To move the cones all the way up and all the way down. Yeah.
I guess that's where slides can come in, so that you can get your whatever type of thing you're using to pick up the cones. You could just kind of pick it up and take it to whichever pole you're gonna put it on, and then you can lift it up using slides and a 4 bar.
Do you know how like tall the linear motion like arms go? Like,
I think it depends on the size. Some might reach farther, while some might just reach shorter.
yeah.